Okay, all right. Well, happy Wednesday. We'll take a look here. I have posted in Canvas under week 3, there is a document midterm 1 topics. So our midterm exam will be this coming Monday. So what's that, October 21? And the description of the exam can be found here. 3 problems, okay? There will be 3 problems on the exam, and that will be it. You will have, I guess, 45 minutes plus 5 minutes for, getting the papers passed out and collected and all of that. I will make a seating chart. I think everybody's seats have like a number on them, right? So I'll try to use those numbers to get them to kind of align. Do your rows have like row letters also? Maybe? Okay, well anyway, I'll some of them do, some of them don't. I'll just have to try to figure out the seating chart and things like that. So I'm gonna send that out. Okay, let me just talk about, okay, let's see. Don't come if you're sick. I'll work with you to make sure you get a makeup and things like that. Nobody wants to be around sick people. Okay. You're allowed a 1 note sheet, okay? Writing on the front and back. It can be handwritten or typed, however you want to do it. Make sure your name is on the note sheet, and that note sheet will be collected with the exam, okay? So, but that's fine. Also bring a calculator. No phones during the exam or things like that. Okay, and these are going to be your problems. We have Bayesian inference with a conjugate prior. So throughout our lecture, we've been doing beta binomial, but you could have any one of these distributions. So I'll have data that comes from a distribution. It could either be exponential, Poisson, binomial, negative binomial, or gamma, all right? So that will be, your data will come from those. And these things, you could go on Wikipedia or whatever. Each of these distributions do have a conjugate prior, and so I will provide some information there, okay? So you'll find the likelihood function of kind of one of these unknown parameters given the provided data. I'll provide the conjugate prior distribution, and then you'll find the posterior distribution of the unknown parameter given the data, okay? And then, so that's problem 1. Problem 2 will be importance sampling. You'll be given some PDF-F, all right? And then I'll provide data from a different distribution G, and then you'll tell me how you use that to kind of estimate, what we want, okay? And then the third problem will be inverse CDF, which we covered on Monday, and we'll cover a little bit more today. And I will give you a PDF, and from there you'll have to figure out the CDF, and then you'll have to figure out the inverse CDF, okay? So, a little bit of integration to go from the PDF to the CDF, and then, working with, I guess, algebra and whatnot to inverse your CDF. And then once you have your inverse CDF, I'll provide random values of U, sampled from 0 to 1, and then you'll tell me what does this translate into, when you use inverse CDF method. Okay? And that's it. Nothing beyond these 3 problems, okay? So it'll be these 3, and that's that, okay? So, okay. We'll take a look at today's lecture here. So yeah, we'll do a little bit more on inverse CDF, and then we'll talk convolutions. But that's that. So, okay. So the way the inverse CDF method works is you want to generate values, random values of x that come from a distribution, and the distribution has this CDF capital F, okay, all right, and presumably a PDF lowercase f of x, and what you have to do is you have to figure out the inverse of the CDF, and then you just generate random values between 0 and 1. You plug that into your inverse CDF function, and those will be your random values of x. The inverse CDF is the minimum value of t such that capital F of t is greater than or equal to u, whatever u value you select, that's between 0 and 1. Okay, here let's take a look at an example here, another example. So we've seen a couple examples. This one would be a triangular distribution. So this is a piecewise function. The value is 0 everywhere except for right here where you have this side. F of x is x, and then over here it's 2 minus x, okay? And then the key is that if you take the total area under the PDF, the total area is equal to 1, and you could check this yourself. But yeah, I mean the length of the base is 2, length of 2, height is 1, and area is base times height over 2, and so that has an area of 1. Okay, so how do we? Is that my computer that keeps? I don't know. Okay, so how do we? First we'll have to figure out the CDF, and then we're going to have to figure out the inverse CDF. So our PDF is piecewise. So figuring out the CDF, we're also going to have a piecewise CDF. So first, we're going to go for values of x between 0 and 1. And so we're going to, our CDF is going to be the integral, from starting at where, our support begins, going from 0 to x, f of t dt. And in this case, it's just x. So f of t is just going to be t. When you take the integral of that, you get t squared over 2, and you'll evaluate it from 0 to x. So you get x squared over 2 minus 0, so it's just x squared over 2. That's what you have for x between 0 and 1. Okay. But now we have to figure out the CDF for values of x between 1 and 2. Okay. So here, the other part, the capital F, okay, the CDF is still the integral from 0 to x, but now we're getting values of x that are between 1 and 2. So here we're going to evaluate from 0 to 1 of t dt, okay? And then the second piece, the right-hand side of that triangle is going to go from 1 to x, and the function there for values greater than 1 is going to be 2 minus x, or 2 minus t dt, okay? So going from 0 to 1, when we evaluate, becomes t squared over 2, and basically you calculate from 0 to 1, and that just becomes 1/2. Okay, that makes sense. That's just the area of this left half of the triangle is going to have an area of 1/2, and then so it's going to be 1/2 plus whatever this side is. Okay, and then so that right-hand side is 2 minus x. So when we evaluate it, it's going to be 2 minus t dt, integral from 1 to x. So we get 2t minus t squared over 2 from evaluated from 1 to x. So you plug in, when you plug in x, you get 2x minus x squared over 2, and then you have to subtract off whatever this is, okay, evaluating from 1, okay, and so that becomes 2 minus 1/2. So this becomes minus 1/2, and so you get 1/2 minus whatever this is, 1/2, and you get negative 1 plus 2x minus x squared over 2, okay, and so that's going to be the right-hand side of for values of x between 1 and 2. So we have our CDF. So we have our CDF going from 0 to 1 is going to be x squared over 2. And then the right-hand side is going to look like this, -1 plus 2x minus x squared over 2. And what this kind of looks like is basically you have kind of this is like a parabola over here, x squared over 2. And then basically you kind of have another parabola that goes kind of like this, right? So this is going from 0, 1 to 2. It's kind of these two parabolas joining up together in the middle. All right, now we need to take the inverse of this, okay? So to calculate the inverse, we are going to set f of x equal to u and solve for x, okay? And again, because our CDF is piecewise, our inverse CDF will also be piecewise. So for values between 0 and 1, our CDF is x squared over 2. We set that equal to u. We're going to solve for x. So this is pretty simple. Multiply both sides by 2. And then you have x squared is equal to 2u. And when you solve for x, you'll get plus or minus the square root of 2u. All right. And in our case, we're going to keep the plus side. But I just have to warn you, sometimes you end up keeping the minus side. So you have to kind of look at like what your values of x are, what your values of u are going to be, and whether it makes sense to keep the positive or minus thing. So in our case, because we know x is going to be a value that's greater than 0, we're going to just keep the positive side. And so we get x is equal to the positive side of square root of 2u. And this is going to evaluate if x is on the range from 0 to 1, this is going to evaluate for u values between 1 and 2. 0 and 1/2. Okay, and then for the other part, okay, for values of x between 1 and 2, okay, we had evaluated this. The right-hand side is -1 plus 2x minus x squared over 2, okay? So we have -1 plus 2x minus x squared over 2 is equal to u. This part's a tiny bit trickier. So solving for x, okay, in terms of u, I'm going to multiply all of my terms by -2, and I will get 2 minus 4x plus x squared is equal to -2u. All right, and then to help me along, I'm going to add 2 to both sides, and that will complete the square on the left, right? So just these little algebra tricks. So now we have basically 4 minus 4x plus x squared, which can be turned into 2 minus x quantity squared. And we have to add 2 to both sides. And then we take the square root of both sides. All right, and we get 2 minus x is equal to plus or minus the root of -2u plus 2. And then again, paying attention to what x evaluates to. So x has to be a value between 1 and 2. So we're going to get values between 1 and 0. So we're going to keep the positive side as well. Okay. So here we'll keep the positive side, and then solving for x, we will get 2 minus the square root of -2u plus 2, and this evaluates to 2 minus the square root of 2 times 1 minus u. Okay, and this is going to be true for values of u between 1/2 and 1. Okay, and that's what we have. So I can plug this in, okay? And so I have two, so I'm going to generate random values from the uniform distribution, 100,000 of these values, and then we're going to say if u is between 0 and 1, we will set x equal to square root of 2u, okay? On the other hand, if u is greater than 0.5, okay, then we're going to use 2 minus the square root of 2 times 1 minus u, okay? So the indicator here is just basically going to be true or false, and so we will replace all instances of x where that indicator is true with basically all of these cases where u is greater than 1/2, okay? And then when you do that, this is what a random sample of x looks like, okay? And indeed, it fits the triangular PDF with values between 0 and 2 following that triangular PDF. Okay, that's an example there. You can also do inverse CDF method for discrete distributions, and it's pretty straightforward and easy. So let's say we have a simple discrete distribution as described by this table, and we can take on the values 1, 2, and 3, and we'll say the the PMF, the probabilities for each of these values are 0.5, 0.4, and 0.1. And therefore, when you think about what is the CDF, you have this piecewise, you have a stepwise function. 0.5. And our values are 1, 2, and 3. And so getting a value between 0 and 1 looks like this. From 1 to 2, you get this. From 2 to 3, you get that. And then from 3 higher, you get that. So this is what your CDF looks like. Okay, so you have the value 0, 1/2, 0.9, and anything where x is greater than or equal to 3, you get your CDF is going to equal 1 because it's the cumulative distribution function. Okay, how do you? There's our picture. How do you inverse this? Okay, so inverting this is a little bit awkward. Okay, but the definition of the inverse is the minimum value of t such that f of t is greater than or equal to u. So if we were to generate, let's say, a random value of 0.326, right? So the inverse is we're generating a value between 0 and 1 of u, okay? And so if I generate a value like right here, 0.326, okay? This should correspond to the value 1, right? So, because we want, basically, anything in this range should be 1, anything in this range should be the value 2, and anything in this range should be the value 3. So how do we turn that into some kind of equation, right? And so when you inverse this, so we want to say 0, 0.5, 0.9. This needs to be 1. This needs to be 2, 3, 0.9, and that's what it looks like. Okay, for values between this is what we have, and so if you think about like, okay, what is 0.326? How do we do this? It's the smallest value of t such that f of t is greater than or equal to u. So the smallest value of t, which would be 1, smallest value of 1 such that when you plug in f of 1, capital F of 1, which would be 0.5, 0.5 is greater than, say 0.326 or something like that. Okay, it just feels a little bit strange because, I don't know, when I was taught how to inverse a function, I was, I don't know how to, it was, the way I always visualize inverting a function is you have this line y equal to x, and then you use that as like kind of this diagonal axis of symmetry, okay? But it doesn't work out this way because if you do that, now you have like vertical lines, which is a no-no in a function. So yeah, you end up getting this minimum value of t such that the CDF of t is greater than or equal to whatever random u value you've selected. Okay, I need to give you your first view quiz answer. So Wednesday, week 3, Wednesday. First answer is D. D as in dog. D. Okay, so we basically just have a piecewise function, and it says, hey, this is the value you generate 1, 2, or 3 based on what random value of u you get. And in general, if you have this kind of PMF where you have a bunch of outcomes and these probabilities such that the sum of the probabilities add up to 1, then your CDF is going to be this kind of piecewise function where you will get whatever your cutoff values are, x1, x2, x3, okay? And then the cumulative probabilities will be 0, p1, p1 plus p2, so on and so forth, sum up to p sub j, okay? And then the largest number will have values greater than that will be your sum is going to equal 1. Okay, so this is how you would generate random values if you know the probabilities of each of these things. Okay, in R, we can do this, and this feels a tiny bit silly. It's a little bit overkill to do it this way, but this will work. Okay, and so we're going to say what we're going to do is we're going to generate a random value u from the uniform distribution from 0, 1, just one of these things, and then if your possible values of x, okay, are 1, 2, and 3 with corresponding probabilities 0.5, 0.4, and 0.1, okay, we have to kind of just check to see, what is the smallest value of x or t such that when I check the cumulative probability, it's going to be greater than or equal to this thing. So we're going to check kind of the cumulative probability from 1 up through whatever position is. We're going to start off with the first value, and we're going to see if that's the case. If the random value of u is greater than that, then we have to go to the next value. But if it's not, then we'll spit out x at that position of u, x at whatever position is. So we start off at the first position, which my cumulative probability is 0.5, and if my cumulative probability 0.5 is greater than u, then we'll spit out x at position 1. Okay, but if like my u is say 0.8, okay, my cumulative probability at 0.5 is not big enough, so I have to go to the next position, position 2. 0.5 and 0.4 is 0.9, and that's going to be big enough for 0.8. And then so my position gets updated to value 2. I'll print out x at that second position, which will be 2. And then here, just kind of for informative purposes, we can see what our random value of u was. So when I run this, I can say, all right, when I generate a random value, if my random value of u is 0.2, that corresponds to the value 1. If my random value of u is 0.68, that corresponds to the random value 2. If my random value of u is 0.916, that corresponds to random x value 3. Okay. R actually has kind of a built-in function. When you use the function sample, you can give it a vector of probabilities. Okay. So here I have x is 1, 2, 3, and I can give it this vector 0.5, 0.4, 0.1, and I could say, hey, sample x. I want 30 of these values sampled from x, where the vector of probabilities is this. And when you do that, it indeed generates values according to those probabilities. Okay, and in fact, if you use this function that we wrote over here, where we took random values of u and had them correspond to random values of x, or the corresponding values of x, and you use the same seed, you get the exact same results here. Okay, so when we say, hey, R, if we do tell R to sample, use their sample function, we get, the sequence 2, 2, 3, 1, 2. And here, if I say, hey, replicate using this random discrete function that we wrote ourselves and replicate it 30 times, and I say set seed 500, same seed, I get the same exact sequence, 2, 2, 3, 1, 2. So this is, I don't know. This is not exactly what R is doing underneath the hood, but it is kind of comforting to know that whatever thing R is doing to generate your random values, we're getting kind of the same results there. Okay, so that is inverse CDF algorithms in R, and that, I guess this would be the end of what will be covered on the midterm, right? So, I mean, because the midterm is really just going to be those 3 problems that I described, where the last topic is inverse CDF, and we saw the importance sampling and the Bayesian inference stuff in previous lectures. Okay, so convolutions, this will wait until exam number 2. Okay, so all right. So what are convolutions? Okay, so convolutions are basically other random variables that are made of sums of other random variables. So if you have random variables x1 through xm, these are independent random variables, then the convolution is going to be the sum of these things. So you're going to have some sum, and then you'll add up x1, x2, up through xm, or whatever these things are. And a lot of random variables that we work with are convolutions of some kind. So classic example, or as a simple example, is the binomial distribution is just a convolution of Bernoulli's, okay? So Bernoulli random variables are basically outcomes of coin flips. You get a 0 or a 1, okay? And we say you get a 1 with probability p, you get 0 with probability 1 minus p. And then if you repeat a Bernoulli m times, now you have a binomial distribution with parameters m and p. So this is like how many times did your coin land heads after 6 coin flips or something like that, okay? Or you repeat the same trial m times, that's that, okay? So, I mean, we have our own binomial random generator, but if you didn't, you could write some code to basically perform your convolution, right? So here we can just say, hey, I'm going to have random values of u, okay, drawn from the uniform distribution, and then we will, if the value is less than p, we will it's equal to 1, and if 0 otherwise. And so here, if I wanted to create my own binomial random generator function, again, R already has its R binom function, but here I'm going to create my own here. We could do it like this. We're going to generate m values of u. So I'm saying R uniform, and then my random variable x, we're going to just start off and set them equal to 0. And then what we will do is, so the x is going to be a bunch of 0s and 1s. And so anytime u is less than p, whatever p I've set, we're going to replace those 0s with 1s. Okay, so now x is going to be a vector of length m, where some of them will be 1 and some will be 0. And it will be 1 where u is less than p. Okay, so therefore the probability that x is 1 for any one of these things is p. And then this thing will return the sum of the x. So we'll get the total number of x's that have been 1. Okay, so if I do this, if I say m is 10 and p is 0.6, I can say, hey, give me a random instance. This happens to be the number 6, but again, if I run it again, we'll get some other random value according to the binomial thing. So here I can run this function replicate, and we're going to say, hey, replicate this 10,000 times, okay? So we're going to do this over and over again. And so now I can say after 10,000 trials, make a table of my random values. And so we're going to get values between 0 and 10. how often did this happen, all right? And so my empirical kind of probabilities will just be what actually happened after 10,000 times. I can compare this to the theoretic probability. So using R's d binom, or basically I could do m choose x, p to the x, 1 minus p to the n minus x, the theoretic probabilities, we can do a comparison. So according to d binom, we should get the value, say 6 with probability 0.2508. Okay, should be that's our PMF. And when we did it 10,000 times, it happened 2,474 times. So we're getting, again, similar, but not exactly the same. But that's it's within what we would expect for random values, right? And then so we're getting pretty similar alignment between what we observed when we did 10,000 random draws versus what we expected. Okay, and here is a bar plot, and what we want to see is the two heights, the empirical and the theoretic heights, to be the same, and for the most part they are very, very similar. Some bars tiny bit taller than the other, okay, but overall, like, these are very similar in heights. Okay, so this is my my table. To compare, if we consider these as kind of so we have discrete outcomes, or we can almost treat them like categorical outcomes, to compare kind of these categorical outcomes and see if the counts match what we expected. We can run a chi-squared test, okay? And so here, the chi-squared test, your two arguments. So this is the chi-squared goodness of fit test, or I guess chi-squared test for given probabilities. And here you give it a vector of counts for each of the categories, and then you give it a vector of probabilities for each of your categories here. So I'm going to take my table of the counts. So this will tally up and say, hey, 0 appeared this many times, 1 appeared this many times, 2 appeared this many times. I'm going to compare it to kind of my theoretic vector of probabilities. When I run this, however, I get a warning. It says, warning, in chi-squared approximation may be incorrect. And that is because when you do the chi-squared test, your expected counts should be at least 5. And in this case, for something like 0, my expected count is only 1 out of 10,000. So that's why I'm getting these errors here. So here, what I'm going to do is I'm going to kind of collapse these categories, and I'm going to just kind of combine some of these things. So what I will do, so if I look at the counts here, the counts, I have 3 and 12 for 0 and 1, okay? And what I'm going to do is I'm going to just kind of combine these two. I'm going to add 3 to 12 here, and I'm going to just get 15. So this is not 1, but this would be like a 0 or 1. So it's kind of like creating an other bin. If you have too many categories where you only have like this category show up only like once or twice, it's better to just kind of combine these really rare categories into kind of an other, or none of the other categories type of thing. So that's what we'll do here. So I'm combining the 3 and the 12 to get a 15. And then I have to adjust the theoretic probability vector as well, because the two vectors, your vector of counts and your vector of probabilities, have to be at the same length. So I have to do the same thing over here as well. And then now I do a chi-squared test between my counts and my theoretic probabilities. And I get a p-value of 0.4675, which would mean I do not reject the null hypothesis, saying at least our data does not we don't have evidence to say our data comes from a distribution other than this theoretic binomial distribution. Okay, and again, just the way we do null hypothesis testing, we can never say it comes, this proves that it comes from the designated distribution, but we're saying we don't have evidence that it comes from something else. Okay, second view quiz answer is the letter A. A as in apple is our second view quiz answer, A. Okay, we have more convolutions, and these are all, they kind of harken back to, I think, when you learned about these distributions in 100B, and it's just kind of like Stats 100B in your mathematical statistics class, just kind of like remembering what the definitions of some of these random variables are. Okay, so the Poisson distribution, if we recall, is how many times does a random event occur within a given span of time, assuming that the random events come from like a Poisson process, basically that they happen at randomly uniform times. And so, you know, the times in between events are exponential. If you look at the distribution of times within a span, it's random uniform within that thing. How many times does some random event occur, though, is going to be a Poisson distribution, okay? So examples would be number of pieces of mail received in a day, number of injuries in a month or something, if you assume these follow some rate parameter lambda, okay? And so if they're individually Poisson random, the sum of them is also going to be Poisson, but your the distribution of the mean is going to be the sum of these lambda values themselves. Okay, so you have so the sum of m Poisson random variables itself is also a Poisson random variable, but with a larger mean parameter. That's where you sum the lambdas here. Okay. The negative binomial distribution, okay? So first, we have to talk about the geometric distribution. The geometric distribution is the number of failures, okay, in a sequence of Bernoulli trials before the first success. So it's kind of like how many times do you have to flip a coin until you see your first head, okay? Or let's say you have a die, how many times do you have to roll the die before you get the number 6, okay? And you might get it on your first roll, or you might have to roll it like 12 times. So that would be the geometric distribution, okay? The negative binomial distribution is to model the number of failures observed in a sequence of Bernoulli trials before the mth success occurs. So this time we're going to roll the die a whole bunch of times until we see the number 6 for the third time, okay? And okay, there are a few different parameterizations of the negative binomial. Some are like how many times do you have to roll the die total, including both 6s and non-6s until you see your third 6, right? So if we're saying like I need to see 6 3 times, you can be like, okay, do we include the first and second time I see the 6 into my total count, or do I not include those? And you have different kind of parameterizations of it. And I'm pretty sure I did this correctly. It's all of these different things you kind of confuse yourself here. But this would be the number of non-6s before we see a 6 for the third time. Okay, and so that you can kind of think of this as just a convolution of the geometric random variables. So you have so basically, you say like, okay, how many times did I have to roll the 6 until I saw a 6 for the first time? And then you just repeat that like 3 times or something like that, okay? And that's what you have. So that's the negative binomial, okay? And we got different kinds of things. So these are all just different kinds of convolutions. Okay, chi-squared variables. You have a chi-squared variable, random variable with 1 degree of freedom is basically you draw a standard normal variable and you square it, okay? So standard normal variable is, and you square that, that's gonna be a chi-squared random variable with 1 degree of freedom, and then if you want chi-squared random variable with m degrees of freedom, it's the sum of those individual things, okay? So if you have a bunch of values from the normal distribution and you square each of them, you have m of them, you add them up, that's going to be a chi-squared random variable with m degrees of freedom. This is just a bunch of these things, okay? All right. We have the gamma distribution. Okay, so we have an exponential distribution, which is used to model the amount of time between random events in a Poisson point process, okay? So if we assume random events occur kind of continuously and independently at some constant average rate, so overall we're expecting, 10 of these things to happen within a day, okay? But they're not necessarily spaced out, so all 10 events are evenly spaced out. Sometimes, a bunch happen together and a bunch later, but overall, on average, we get, 10 of these events per day or something, okay? The time in between events is going to be exponential, okay? And then the gamma distribution could be the amount of time until the, the nth occurrence of an event, right? So between, if we just start now, what's the time until the next event? That would be exponential, but then we can say, hey, what's the time until the event happens 3 times or 4 times or 5 times or something like that? That's going to be gamma, and that's going to be the sum of these IID exponential things, okay? So the gamma distribution is a convolution of exponentials, so we're just going to say, okay, this is just one of these things. I mean, these kind of naturally just fall out of their original definitions, right? So you say, okay, well, exponential is just for the next event, and you say, okay, well, I want to wait 3 events. Well, it just makes sense to just add 3 exponential things together. And that's exactly what we're doing, okay? So that's the gamma distribution with parameters m and rate parameter lambda. All right, the beta distribution. So remember, the beta distribution is always going to be something between 0 and 1, okay? And there's several ways you can express a beta distribution. But one of these ways, okay, is if you're going to have a beta distribution with shape parameters a and b, you can just generate a whole bunch of exponential distributions with shape rate parameter 1, okay? A total of a and b of these things, and then the beta distribution is going to be the sum of the first a divided by the sum of all of them, a and b together, okay? And that is that's going to follow a beta distribution. One thing you have to be kind of careful, because I've seen students make this mistake, is that they generate a random values for here. So like, let's say a is 5 and b is 6, okay? So a and b added together is 11. And I've seen students make the mistake of generating 5 random exponential and adding them up in the numerator, and then taking 11 random exponential and adding them up in the denominator, okay? But that's that will sometimes lead to, by random chance, where the sum of the numerator is greater than the sum of the denominator if you generate them independently, okay? So that's not going to work. What you have to do is you generate just 11 altogether, okay? And then you take the first 5, a subset of that 11, and that's going to be the numerator, and the denominator is going to be the subset, the sum of all 11. And that way, this quantity will always be less than 1, okay? Because the numerator is always a subset of the denominator, okay? Because otherwise, if your beta, a random beta is generating values greater than 1, you've done something wrong, okay? You can also, because this is just a sum of exponentials, okay, you can also treat it like a gamma, okay? And you have gamma, and again, here you can't generate one gamma with a U and a second generate another gamma with parameter U plus V. It has to be like basically the U is like your first A, and then the V is going to be like from the remaining, B values. Okay, so the numerator always has to be smaller than the denominator there. Okay, and then the t distribution is based off of this. You have a standard normal on the numerator, and then in the bottom you have the square root of this chi-squared thing, which is kind of weird. And this is the t distribution. It's always like, it feels so strange, but it's basically you're kind of attenuating this normal distribution, so you have thicker tails. But this is, again, because chi-squared is a convolution, you can also treat this basically as kind of a convolution of a random variable here. Okay, and that will be it for today's lecture.